I don't want that part. I'm sorry. I'm trying to make a podcast, so. Oh, hi everybody. This is Mr. Folly, and welcome to podcast 11.1. We have a ton of objectives that we're going to do there, so I'll let you look at those and be all excited about that. So, identify, blah, 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 define, define, define. So, look at those, read through them, hit pause. I'm going to move along. So, all right. Iron plus oxygen yields 2 iron 3 oxide. If 4 moles of iron react, how many moles of oxygen react? Well, looking right there at my coefficients, I would get 3 moles for every 4 moles of iron, so it's just 3 moles of oxygen. If 2 moles of iron 3 oxide form per minute, so 2 moles of this form per minute, how many moles of oxygen disappear per minute? So again, look at those coefficients, 2 moles, that would be 3 moles of oxygen. Now notice here, this is per minute, so that's what makes it a rate, is putting it per time. If oxygen disappears at 5 molar per minute, what is the rate of change for iron and iron 3 oxide? Well, I'm just going to do iron 3 oxide because that's more fun. So for iron 3 oxide, so times dividing bar. So this one's a little bit different because I can't look right at the coefficients to get it. So moles of O2 and moles of Fe2O3. I still have that relationship of 3 to 2, so 3 moles of oxygen to 2 moles of this, and I would get 10 thirds, which you'd never leave that because I don't want to watch my sig figs, and I get 3.33 moles per minute. And moles of what? Fe2O3. So another simple little mole ratio that we just can't seem to get away from. Rate is measured in change of concentration per unit time, typically molarity per minute. So how does rate compare to time? Okay, so rate and time are inverse relationships. So as one goes up, the other one goes down. So run to class. So if I run fast, my time is low. Oops, not slow, low. Time is low. If it takes a long time, then I'm moving slowly. Okay, so they're opposites. Collision theory. In order for action to be successful, meaning that it actually happens, so in order for particles to collide, particles must collide, bam, with enough energy, bam, and the right orientation. So I think of this like home run derby. Okay, so in home run derby, the batter has to hit the ball, bam, but he could hit it and it could be a little dribbler and grounder that goes nowhere, or it could be a foul ball. But it has to collide with enough energy. Doink! Oh, look, it got all the way to the first baseman. And then the right orientation. It's got to be lined up correctly so that you get it in the right spot. All reactions do this, even decomposition reactions. So all reactions, this is the collision theory. Particles must collide with enough energy and the right orientation, which sounds easy, but it doesn't happen that way very often. If I look at this example, I've got Bruno and Bruno, and if I want 2 Brunos to make bromine and no-no, if it's lined up like this, see how these could hit and I get 2 Brs, and these could donk, donk, and I get NO and NO. If I have this lined up this way, that could happen, it would be great. But if I had it lined up this way, there's no way I could get Br to join with Br. Okay, so there's going to be no reaction. And if you think about it, this is rotating them at a 90-degree angles. There are bajillions of ways to orient these things, and they have to be pretty much right on with enough energy. So the success rate is low. Imagine if I put 10 pen caps and 10 pens in a box, and I was looking to see how many caps fit on the pen by shaking the box. So here's my box, here's my pen, and then I put in a pen cap, and I just put the lid on the box and I shake it. Is it likely these two will hit each other? Yes. Now if I shake it really hard, could they hit with enough energy? Yes. But is it likely they hit with enough energy and the right orientation so that my pen cap goes right in there? It's not likely, but if you do it often enough, eventually in a bajillion years, you might get it to work. I can change the rate of reaction by temperature. I'm going to talk about increasing each of these. If I increase the temperature, I will have more collisions. Right? Because particles are moving faster, I'll have more collisions. I'll also have more energetic collisions. And a lot of collisions happen that don't have enough energy. And this one is way more important. Concentration. If you have a greater concentration, that means things are going to be closer to each other, so there will be more collisions. By the way, both of these make it go faster if you increase it. So again, if I increase concentration, there'll be more collisions. So it will be faster. If I increase surface area, so the way this could be increasing surface area is if I have a cube, oh, great art skills, and if I cut it in half, then that area, if I cut this in half, then this inside piece and that inside piece is now available to be struck. So that increases surface area if I cut it in half, which increases collisions because there's more spots to collide. I just misspelled collisions. Sorry about that. Catalyst inhibitor, what that does is it lowers, a catalyst lowers the energy needed. So you get more collisions are effective. Remember I said that temperature part, the effective collisions with enough energy is very important. That's why catalysts really, really change the whole deal, where reactions go so much faster. Reactions occur in step, like baking a cake. Step 1, mix it. Step 2, bake it. Step 3, frost it. Now mixing it, let's say that takes about 2 minutes. Baking it, let's say it takes 20 minutes. And let's say frosting it takes 2 minutes. And let's say I have to make 1,000,000 cakes. Beep, beep, beep. I'm hungry already. Lamb cake. So the rate determining step is the slowest step and controls the rate. The reason why it controls the rate is if I'm making 1,000,000 cakes, if I found a way to change 20 minutes into 15 minutes, I've just saved 15 million minutes, right? Because this step right here and this step right here don't have that impact. But while I'm waiting for my cake to bake, right, that 20 minutes, can I make a bunch of frostings, right? I can get ready frost and have all that time, so I won't be waiting around. And that mixing, I can pre-make the mix while I'm waiting around for that to happen. So the rate determining step is the slowest step and controls the rate because other steps wait for it. And they have to wait. So the rate determining step for making a cake is baking it. The nature of reactants also control the reactions. This refers to the complexity of molecules. It can make a reaction slower or faster. So if I was trying to build a house out of this, and this is complex, it would be slow. If I were to make it out of this, which is simple, yay Lincoln Logs, it would be fast. So simple things react faster than other things. Delta H is enthalpy, and we've seen this a handful of times, which is basically heat. If heat is on the left, it is endothermic. If heat is on the right, it is exothermic. Remember, endo means into, so into reactants. Exo is out of reactants. If it feels cold, it's absorbing heat from me, so energy is going into it, so it's endo. Boiling water this is tricky, endo, because heat goes into water and is absorbed to boil. Energy diagrams. Okay, so reactants, wherever you start with. Products. Now, products can either be low or high. Okay, I'll do an exothermic one first. And what happens is there's always a hump in here. Okay, hence the Humpty Dance. So reactants, products. This right here is a physical thing called a transition state. And this is my potential energy, so this is energy, and this is progress of the reaction or time. Those are my axes. The activation energy is the energy from the reactants up to the top of the hill. Okay? Delta H is the difference between reactants and products. And in this case, it is exothermic because the reactants lost heat as they became products. So there's one that's exothermic. If I were to draw one that's endothermic, it would look like this. Again, reactants, products, delta H, that's EA. That thing right there is a transition state. I thought I maybe had room in there. Fast or slow? And this is where catalyst inhibitors work. So this is potential energy, this is time, basically. And if I have a reaction here, fast or slow, the higher this hill, the slower it is. So high hill equals slow. So what a catalyst does is a catalyst breaks a new path, so it changes the activation energy. Remember we talked about how important the energy is? This is the activation energy normally. This is the activation energy for the catalyzed reaction, cat EA. Okay, so the catalyzed EA is lower, so the cat makes it go faster. Okay, now if I had an inhibitor, same type of deal. An inhibitor would make it go slower, so it would cause a higher hump. Bonds break and absorb energy. You've heard this before. Bonds break and absorb energy. Bonds forming releases energy. BARF. Break, absorb, release, form. If energy of formation, remember formation is released. So if you release more, the reaction is exothermic. If the energy of breaking or breaking is absorb, the reaction is endothermic. Energy diagrams in terms of bonds. So, whoops, okay, that's just empty. Okay. So as I go from here to here, what's happening here is breaking bonds. Alright, so here are my reactants, and I'm breaking bonds. And then when I'm losing energy here, all that right here is forming bonds. Can I write sideways? No. Oh, almost. Okay, forming bonds. Exothermic is favored in nature. Lower energy is favored. High energy is high stress. So you want to be on a beach with its low energy, not high energy. Ah, we're all going to die. Run! Disorder is favored in nature. Do buildings build themselves? No. Nature tears them down. Do things fall apart? Yes. Nature tears them down. Look. Hi there. I'm nature. I'm going to tear you down, building. And that's what happens. Do papers write themselves? No. And houses of squalor do not clean themselves either. So review. Rate is measured in molarity over time. Time is the opposite of rate. Not quite the opposite, but they are inverses of each other. Home run derby is the collision theory. Reactions occur in steps. The slowest step is rate determining. And complex shaped short-down reactions. And there you go. I will talk to you later. Toodles.